Today, I'm gonna talk about a special neural network called Generative Adversarial Network. And before we jump into the topic, I'm gonna to show some of the examples of this neural network. So let's do the first one. I just tapped into this person doesn't exist. So if you look at this image, it looks so real. Probably you guess it's a photo of a person, a real person, but it's not, because from the website, the name of the website is "This person does not exist." So this person does not exist. It's generated by computer. I can show another person and another person. They look so real, but they are not. They are faked. They are generated by computer. So we all know that computers are good at generating random numbers, but not many of us knew that a computer is also good at generating random faces. Computer can not only generate faces, but they also can generate videos. So I'm going to show a YouTube video. Probably some of you already watched this video.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right, or Ben Carson is in the sunken place. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. That's a time when we need to rely on trusted news sources. It may sound basic, but how we move forward.
So I'm not going to, let it go for the whole video. If you like, you can search on YouTube. YouTube, you can find a lot of similar videos that are actually generated by computer. So when I first watched this type of video, I was shocked and also kind of worried that because I was worried that this technique might be misused. But today I'm going to talk about the generative adversarial neural network, which sits at the core of this technique called a deep fake. So today the material is mainly from TensorFlow official website. I'm actually use one of its tutorials. And if you are serious about the generative adversarial network, I would suggest you to read the first paper about the GAN. GAN is the short for Generative Adversarial Network. This paper is authored by Ian Goodfellow in 2014. And if you want to read a more advanced, development, you can read papers depending on what you want. For example, if you are interested in face synthesis, you can read this paper written by a group of researchers at NVIDIA. And so let's see the tutorial that I take from TensorFlow website. The reason I'm going to use the tutorial is that it's short and simple enough to illustrate within an hour, but it also illustrates the basic structure of GAN and how it works. So the goal of this case study is to generate digits 0 to 9, so that they look like being written by a human being. So the method, yeah, again, is GAN. And we are going to use the TensorFlow as the machine learning platform and Keras as the interface. The data set is called MNIST. So on the right, you can see some examples here, okay? So the basic idea of GAN is to create two rival networks. So, and let them compete or battle against each other. One of the neural network is called a generator, which tries to generate something of interest. For example, money bill. And his goal is try to make the bill looks like real as possible. And the other network is called discriminator. And his role is try to detect those faked money, okay? So these two are battle or compete against each other in the training session so that both of their skills, I mean, for the generator, their faking skill, or for the detector or the discriminator, detecting skill get improved. So that's the whole idea. So take an example of, cat detection. So the generator generates something, here. Say this is a cat, okay? But it cannot fool the discriminator. The discriminator finds it's not. But the next stage, the generator generates better than the first attempt, but still cannot fool the discriminator. But as it's going on, eventually the generator will generate something that really looks like a cat. And this time it successfully fooled the discriminator. So this is the whole idea behind the generative adversarial network, okay? So before we jump into the code level to illustrate how GAN works, so I want to introduce some component of the GAN so that later on it's easier for us to understand the code, okay? So one of the layer I'm going to use in this tutorial is called a dense layer, or also called fully connected layer. For every neuron on the dense layer, it has a connection, one connection with every neuron in the previous layer, something like this. There is a weight associated with each connections. So how to calculate the output of the neuron in the dense layer? It will do this formula. Basically, you multiply the weight with the input, and then you sum up the products, and finally you can plus a BIOS, but this step is optional. You can use BIOS or not, okay? So we can do this for the next one, calculate in the same way, and so on and so forth until the last neuron in the dense layer. And we do the similar calculation. And basically, if you look at this formula, you can see that it's pretty much can be expressed in matrix and vector multiplication. And that's why a GPU is used, and GPU is really good at do the matrix versus matrix, or matrix versus vector multiplication. So in this dense layer, the trainable variables, that are the weights, and also the BIOS if we are going to use the BIOS. Okay. And another concept is a convolutional layer. Suppose we have a kernel or a filter 3 by 3, and we also have an image, but here I just show a very small image, only 4 by 4, but the basic idea is the same. So if we apply convolution between the filter with the image, we will get the result is like this. It's a 2 by 2. How we get this 2 by 2 result? The way we do it, we place the filter on the image. We start it with a line on the top left corner, and then we slide to the right each time and down each time, and we actually slide through the filter across the image. At each step, we do the element-wise multiplication and sum up the products. So let me illustrate furthermore. Okay, so here you can see that the first step, I overlap the filter here. Probably I can use this. Oh yeah, I overlap with here, so I can do element-wise multiplication. -1 times 3 is here, -1 times 0 here, -1 times 7 here, and then the next row 0 times 8. You can see I don't want to repeat those. So when I do all the multiplication and sum up the product together, I'll get -4. And I put number to here, -4. Then I move the whole filter one step to the right. So now I will get somewhere here and repeat the process. Do the similar thing I got, I will get -6. And do the similar thing, the one move down, one move the filter over this region, I will get -6. And finally, when I move the kernel to the bottom right corner, aligned with the bottom left corner, I will get -2. So this is what so I'm gonna, so this 4 -4. So the whole process is something, so right now it's, I got if you see the cyan, I just got to the top left corner calculated. Then the animation will show how we calculate the rest 3. Just move it to the, each time we move one step. So the step in the jargon of TensorFlow, we call it a stride. Okay. Okay. So so this is a typical no padding stride. So as a result, we got our 2 by 2, but the input image is 4 by 4. How to keep the dimension unchanged after the convolutional layer? We can use the padding. So we can pad along the boundary and with zeros. So then we can get the same size. You know, you see the light blue is the original. Sorry, let me show. Light blue is the original image, and the cyan is the output image. They are the same size now. So by using padding, okay. Another confusing concept is transposed convolutional layer. And because some people said this is a deconvolutional, it's not. Conceptually, it's not deconvolutional. It's just transposed. So now I show a normal convolutional layer that I showed before. And if we transpose it, we will get something like this. Just reverse the process, okay? So this is the way we do transpose. So why we do transpose convolutional? The reason is we can, enlarge the dimensions. So for example, you see in the transpose, the input is 2 by 2. And by padding, we can get a 4 by 4. So we can enlarge the dimension. So that's what we want in the generative network, okay? In the generator, okay? Another one we want to use is use stride. Instead of 1, we use stride 2. So this is another way we can increase the size of the output images. So this is a normal convolutional layer. If we transpose it, we will get something like this. Okay, now 3 by 3 becomes 6 by 6. Okay, so later on, shortly, I will show the code. But here, I just want to show the structure of the generator and the discriminator. So let's first take a look at the generator, because it contains so many layers. Without jumping into the each layers, let's just take a look at the input of the whole network and the output. So the input is just, the first one I use a question mark that indicates the size of the batch or the number of samples in a batch. Because it is unknown, we just use a question mark, okay? It could be 100 or 200, either way. So it's just, what I'm gonna to point out is 100. Here, the whole network, because this is a generator network. So the whole point is how to generate a digit from nowhere. You got from something. So here I define 100 numbers or a vector of 100 numbers. So then the output is from the 100 numbers, I can determine a 28 by 28 image that shows an image that looks like handwritten digits, no matter it's a 0 or 2 or 7, whatever. So it should look like a digits, especially a handwritten digit, not a printed image digits. Okay, so the thing to understand the whole thing is you just imagine that like our gene control our traits. You all know that our genes control our skin color, hair color, or even our body shape. Here we have the 100 something like a code, just like our genes. We can control the appearance of the digits. Not only the interpretation, recognizable digit, whether or not it's 0 or 1, but also the different representation of the same digit. For example, if you write number 2, it's quite different from the number 2 that I wrote. Okay, so that's something that I want to point out. They're all determined by the 100 genes coding. Okay, and the decoding is just the discriminator is just the other way. So you input an image. It could be either a faked one from the generator, or it is a real handwritten digit image. You put the 28 by 28 grayscale times 1 means grayscale, because only one channel. If it's colored, it should have 3 channel is 3, because each channel represents R and G are red, green, and blue. So now only one is a grayscale, okay? And I'm also gonna talk about the output. You see the output is just one single number. You probably guess, okay, because this is a discriminator, probably the output number is either 0 or 1, it's binary. No, it's not. In this case, it's just a real number. We call logit. The reason is we want to the network to output a real number. The larger it is, the more likely is the input image is a real one. The smaller it is more likely to be a fake image. So we call this real number a logit. And later on, we will, convert it. You see how to measure the output performance. I will illustrate later on. Okay. And the next, and also in the example, it uses a loss function called a binary cross entropy. And the loss function is actually measure the performance of these two neural network. And we want to use the loss function to measure how many mistakes, how much of how well they perform. So here we use like I mentioned earlier, the output is a logits. Okay, we need to convert those logits to probabilities by using a sigmoid function. So this sigmoid function actually makes them looks like makes the convert the L. Suppose L is the logits, the output from the discriminator. Use this sigmoid, we actually map the value L into a value between 0 and 1. So that's good because the probability should be below 1 and greater than 0. Okay, or maybe include 1 and 0. And if we have the Q1, means what's the probability the input is a real one. And then Q0 is the probability the input sample is a fake one. So we just use the one math, the Q1, because there are only two possibilities, either true or false, okay? So then we apply the cross entropy, the usual way, okay? So that's the some introduction, some preparation. So now it's time to jump into the code. So I'm gonna log on to Graham CD project. Yeah. So you can see that I actually downloaded the notebook of here from TensorFlow website, and I converted it to a Python script. And later on, I do manually tidy up of the code, and I got this file. Okay, and today I'm gonna show the batch file, the job file. Actually, I'm gonna run it on GPU. So basically, I just run the cleanup version of the Python script. So let's take a look of the code. So the first part is import something. I import TensorFlow as a backend, and I use a TensorFlow interface. I just use the layer part. First is ignore those small, this session, I just import some modules. And first of all, I define the batch size that I'm going to use in the training is 256. And this is the 100 is the input dimension that I mentioned, the magic, the 100 magic number as input to the generator, okay? They act as a gene, okay? So the first step is I'm gonna load the data and reformat. I just use this convenient function, and I'm gonna just use the first part of the training data. I ignored the testing data, and now I'm gonna reformat the image, because when I first loaded the training image, actually each image is not an image, it is a vector size of 784. So I need to rearrange the 784 elements into 28 by 28 so that they are so that I need to reshape them so that they look like 2D images. And secondly, I need to change the image value range because this is a grayscale image. The original is from 0 to 255. So I do this. Actually, I remap it. So mapped it to -1 and 1. So it's actually a normalization work. So lastly, I shuffle them and batch them. So basically, I got remember this train underscore dataset. This is a irritable variable that you can use in your for loop. Each time you can get a batch of 256 samples. Okay, so to remember train underscore dataset. That's all we want to know. Next, we are gonna create the generator. We call this function called the make generator model. So basically, because we are going to use the class interface, we want to build the layer sequentially. So we use this one. So each time we add, for the first one, we add a dense layer. So you see the input shape, we defined the 100 numbers. And the output is 784, which is 7 times 7 times 256, okay? The next layer is a batch normalization. Is used for, reduce the effect of overfitting. And the next one is activation function. Here we use a leaky reload. And after that, we do a reshape, because previously the number, is not the output is a vector. We want to convert it to an image 7 by 7. Remember, the size is not 28 by 28. So all the numbers are designed specially 7 by 7, because 7 times 4 equals 28. So remember this special number. So we reshape this 7 by 7 image. It has 256 channels. Okay. So after that, we have transposed the convolution layer. And because we use strata equals 1, 1 along horizontal and vertical directions, so it won't change the size at all. So after that, it's still 7 by 7. But because we use 128 channels, afterwards 128 filters, the result we have 128 channels. Okay. So after that, still batch and leaking, because those two doesn't change the shape of the output. We don't mention them. And then we do a convolution again, but this time transpose the convolutional layer again, but this time we use the strat 2 by 2. So that means we will double the size from 7 by 7 to 14 by 14. And also because we use 64 filters or kernels, the result, we have 64 channels. And after the same thing, apply those two. And finally, again, we have another transposed convolutional layer. And because the stride size 2 by 2, That means we double the size. From 14 by 14, we got 28 by 28. Okay, so that's the model which will return. So we call this function, and we got our generator. So this, remember, generator is the network of we just created. Okay, and now we define the how to create a discriminator. Similarly, the first layer, we use the convolutional layer. And the input is a 28 by 28 grayscale image. After that, we have reload activation. Dropout is a special layer, is also used to reduce the effect of overfitting. Not to prevent, because you can never prevent overfitting. You just reduce the amount of overfitting. Okay, so after that you apply another stride, and so let me explain. The first one reduce the size 28 after this stride, it becomes a 14 by 14. And then after this one, it becomes 7 by 7. So after 7 by 7, and we want to have a dense layer. Before that, you should convert the 7 by 7 image format into a vector. So you flatten it, just like a reshape. So previous reshape, in the previous reshape, we do from vector to a 2D array, but here flatten just do the opposite, from 2D array into a one-dimensional vector. Okay, so now we call this function, get our discriminator. Okay, after that we define our loss function. We use this binary cross entropy that I have just described in the slides. And once we got everything ready, we need to define the loss. So we use two functions. One is define the loss for discriminator. So you see, we passed into two arguments. The first one is the output of the discriminator when we feed the real image into the discriminator. And the fake output is the output of the discriminator when we feed the neural network discriminator with a fake images that are from the generator, actually, in our case. So once we have those two, how to measure? So for the real one, we want the ground truth is 111, because 111 represent they are real. And for the fake one, I hope the ground truth is 000. Okay, so we created the function like a TensorFlow TF dot once, like it's create a vector compose all ones as its element. And like means I want to use this dimension, the size just like this one, not the contents is different. Okay. So after that, we measure the loss for the discriminator based on how it reacts to the real image and how it reacts to the faked image. We want them. We want the discriminator reject every faked one and accept every real one. But in reality, it's hard to achieve this. But the total loss is the mistake they make in the real one, the mistake they make in the faked one. So we sum up together. That's the loss for the discriminator. For the generator, it's different, because we only care about how the faked one can fool the discriminator. So you can see you only care about the fake output from the discriminator, and we want to see how much it will being accepted. You see the difference. Can you see the difference between these two lines, this line and this line? The last two is faked, but the faked in here, it will be good one if I all classify as 0. But here, for the generator, I want just the opposite because they are rivals. For the generators, I want all the faked output are accepted as a 1, you know? So they are just the opposite in this way. So after that, we need to define 2 optimizers for each of the networks. So they are to, these 2 networks are to be trained separately, okay? After that, this part is to define the checkpoint. So you can save the intermediate training result, but it's optional here. I'm going to just skip it. Now I'm ready to train it. So the training part is I'm gonna train 50 epochs, and each time before training I'm gonna generate 16 random numbers as a seed, so that I use them as input to the generator. So I always I use the 16 as a test object. So I always want to check to see these 16 100 numbers, how, if we feed them into the generator, how well the 16 image generated will look like a real digits written by a human being, okay? So the training step, we define a function here. So it's something, you know, we give a real image from the amnis data set, which is the one that I previously already prepared well. So I just go back. So this should be this one later on, the irritable, you know, batched data set. Okay, so let's go back. So so here first I generate some input, a random input size of batch set, which is 256, as input to the generator. I call it a noise. If I pass the noise into the generator, it will give me 256 faked images. Okay, so that's the way. So basically, I'm going to calculate the gradient for both of the networks. So the first one, I use the image. I use training. Say I'm not only generate the image, but I'm going to train those trainable parameters. So secondly, I pass the image. You see, I say this image is from the real amnis data set. They are real images. Okay, I pass. I got the output, and the faked images here I also pass into the discriminator and let it get a faked output. Okay, so I got those two, real output and faked output, and after that, I'm gonna measure the loss for the generator and the discriminator, because generator only care about the faked output and the discriminator care about both, okay? Once we got the loss for both, we pass them, we calculate the gradient. This is the way it does it, okay? How they calculate the gradients. And then finally, once we got the gradients, we applied the gradients, the generator of the gradients, we apply the gradients to both of the networks. So this one applied to the generator and this one applied to the discriminator. So here, if you are not familiar with neural network, you know, neural network training is composed of forward feeding So and the back propagation, forward feeding, you feed the data into the network and go forward and get the result. And the back propagation is you calculate the gradient and you propagate from the last layer to the first layer. In such a way, you update the parameter, the trainable parameters. Okay, so those are the detail which are handled by TensorFlow. So you don't need to worry about those details. So once we know how we define a function that handle a single step of training, we can go through a loop. We call it training. So in this, we just the outer loop is a loop through the epochs. We are gonna loop 50 times. And for each epoch, we loop through batches, okay? So for each batch, we just call this function, that's all. So simple, okay? And next, we are gonna save the images of each epoch. So use the seeds, as I mentioned earlier, we create 16, random seeds that we can generate some random images. We see how it works. So so here it is. Let me, where is it? Okay, here. So we pass the seed, the generator, and so the function is below that I'm gonna to show. Sorry, this one I'm gonna to show very soon. Okay, so now I'm almost done. So I'm not still I'm talking about the training function. So basically, two loops. The inner loop we'll call train step, and we save it and we save another image. That's pretty much it. And now take a quick look of how we can generate and save the image of 16 test image. So basically, the model is the generator. We pass into the test image. Okay, is the seed. And we say training. No, we don't want to train. We just want to generate the. It's just a feed forward, no back propagation. We got the faked images. Then we are gonna display the faked images, 16 faked into a 4x4 tiles. And then we are gonna show them. Okay, so we save them. Those are details. I'm not gonna. So this is the main function. Call the train that we defined here. So we call the train, pass the iterable data set, say we are gonna run the training 50 epochs. So now the later on is a checkpoint thing, and the last part is how to synthesize all the images that we generate along the training process into a GIF animated images. That's another detail I'm not going to illustrate. So this is the overall structure of the data, the code. So I'm gonna submit the job, let it run. And in the meantime, I'm gonna show some result because let me see if it run or not. Okay, it's running. So all right, it takes about 7 minutes to finish. So in the meantime, let's see if we have some new. No, probably I can see some. I got some old result. There, something there. Okay, so I can show some image here while we're waiting. This is some result from my previous running. So I just display. This is the image that I generated after first epoch. So you see, it's very rough one, doesn't look like digits at all. I can show the second one if you want. Still not very well. But if we jump, instead of 1, 2, 3, we jump to 20. Sorry, 20. Kind of better, but not good enough. But if we display the last one, let's see, 50. It's much, much better. Although you may argue that some of them, it's hard for us to tell whether or not it's 2 or 3 or something or 7. But still, but it's already show the, it's mimic our handwritten digits pretty well. But if you want to further to improve the result, I think you need to either, change the architecture of the generator or the discriminator so that you can, but because the purpose of this tutorial, this webinar is to illustrate how generative adversarial network works. So I think that's good enough. So I'm gonna stop here. Let's go back to see if my running is finished or not. Probably not, but at least we can see some results coming in. And yeah, so I'm gonna stop here.